Grade 12 chemistry in the Canadian curriculum, and well, pretty much North America in general, because unlike math, we basically share the same chemistry curriculum. Grade 12 chemistry begins with organic chemistry. So we start with the simplest organic compounds, and I hope we have all had experience with organic compounds. Why? Well, okay, the human body is mostly water, yes, but there are plenty of proteins and lipids of various types, such as cholesterol, which keeps cell membranes fluid and not too fluid over a very long range of temperatures, and phospholipids, which actually make up the main bulk of the membranes. And there's, of course, triglycerides, and there are plenty of other lipids. Triglycerides being fats, which are used for energy storage in animals and also in plants. When do plants use oils for energy storage? Well, there's a few occasions. One, when they maintain an oil droplet to control their buoyancy, although that's more buoyancy and less energy storage. There's also the case where a plant will need to move. This is not fiction where trees can get up and walk. Plants move. How do plants move? Well, if you've ever seen a dandelion seed blow by, first of all, that's technically not a seed because it was not formed by sexual reproduction. But the point is that seeds contain oil, or seed-like things also contain oils, because that has much more energy per unit mass than starch, which is the usual storage medium for plants. Animals use glycogen, which is a little bit more efficient than starch. Storing energy as fats is less efficient than as sugars, but we'll get to that at a much later point, and really that's for mostly biology. So, we are all very intimately familiar with organic compounds. And what are organic compounds? Well, okay, you've probably read this by now, but it's a compound that contains carbon. It's a molecular compound that contains carbon because there are other compounds such as, say, tungsten carbide, which is used in armor-piercing shells that do not use depleted uranium. And of course, there's other stuff like titanium carbide and such. But those are ionic compounds. So we're looking for molecular compounds of carbon, not including carbon monoxide, gas, and carbon dioxide, gas, under normal conditions, and hydrogen cyanide, which is also a gas under room temperature. Now, why are these three not included? Basically, convention. Carbon compounds tend to contain hydrogen, and sometimes they contain oxygen, and sometimes they contain some nitrogen too. So, if we're going for the simplest compounds of carbon, then you'd think, hey, long carbon chains with something sticking out the side. Or rings with something sticking out the side. And if you think this, you would be right. The simplest compounds are hydrocarbons. The simplest organic compounds are saturated hydrocarbons. Why? Well, wait a second. If we have, a long string of carbon and hydrogen sticking out the sides, sure. If we have some parts where, there's less hydrogen here than if it was all just uniform, then that would be more complex. So the simplest, the one we start with, is an alkane, which is a hydrocarbon, a compound containing only carbon and hydrogen atoms. Hydrocarbon. Sounds pretty obvious, right? If you think about it, hydrogen, carbon, done. That's it. Nothing else. Stuff like glucose, a sugar, is not a hydrocarbon because it has oxygen in it, hence carbohydrate. So the base formula for most sugars is CH2O. So that's the empirical formula, which is a concept we'll cover a little later. Now, a saturated hydrocarbon has only single covalent bonds between its carbon atoms. So each carbon atom, in addition to holding on to neighboring carbon atoms where applicable, so say the end member of the chain has only one carbon to hold on to, and it's holding on to as many hydrogen atoms as it can. Now, carbon is capable of forming 4 bonds. If we look at our periodic table, we can figure out that carbon is capable of forming 4 bonds. So, an alkane, a saturated hydrocarbon, the simplest alkane would be carbon, hydrogen, 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 and hydrogen. So, methane. Of course, we should technically draw this further out, but this represents the point where we can do a Lewis diagram where we show the electrons are shared in these 4 covalent bonds. Alright. So, a cyclic alkane is a more complex version of an alkane. It has a ring structure. Now, how many do you need to make a ring? Okay, if I have a carbon here and I have a carbon here and they're linked together, can I bend that into a ring? No, that bond is straight. So, you'd need at least 3 to make a ring. The simplest cyclic alkane is... Cyclic is also okay. It's tomato in terms of pronunciation. It is cyclopropane. Now, cyclopropane is very unstable because the typical bond structure for carbon is tetrahedral. If you've seen a tetrahedron, that's 4 identical equilateral triangles put together to make a shape. And a tetrahedral bond arrangement is 1 atom at the center and sticking out to the 4 corners. Which means, well, cyclopropane, the angle here, instead of being around 104.5, although there are a few bonds that, depending on their various differences, do get to, say, 109 or 101 or similar. There are several different bond angles that can be possible. But wait a second. All of these are about 104.5, like, say, ammonia and so on. First of all, ammonia doesn't actually have the same bond pattern. It has the same orbital pattern when it works it has the same orbital pattern as carbon does, except it has a lone pair sticking out the top where carbon has a bond. Now, these angles are all around 105, 104.5-ish. Wait a second. If you have 3 members in a ring, that's equilateral triangle. That's 60 degrees. How much effort do you think it takes to bend 2 groups of electrons inward from being 104.5 degrees apart to being 60 degrees apart? Given the very close space and the amount of strength and electromagnetic force exerts relative to the charges involved, this takes a huge amount of energy, so cyclopropane is very unstable, and if you add anything that kind of reacts-ish with this stuff, it will burst apart. So it will react. Now, we do point out that most alkanes are actually relatively unreactive. So an alkyl group is 1 or more carbon atoms that form a branch off the main chain. What is the main chain? Well, say we have a carbon backbone that looks like this. So 1, 2, 3, 4, 5, 6, 7, 8, that's an octane. The main branch here is an octane. And then say we stick 1 methyl group, we call this a methyl. Now wait a second. If we call this methyl octane, what do we know about that? Well, it could be sticking out from the middle, it could stick out from here, anywhere except at the very end. So, what do we number this? Well, 1, 2, 3. So this is on the 3rd carbon. We number starting from the end that ends up giving the smallest total number for your substituents. So here there's only 1 substituent, so it's 3 methyl octane. On the other hand, if we had, say, this, then that would be, instead of 3, we would change this to 6, 7. No, We do not do this. We start numbering from the other end instead. So instead of 3-methyl-octane, we would have 2, 3, 1, 2, 3, 4, 5, 6, 6 trimethyl. Octane. There are 3 methyl groups on this octane. And their positions are at 2, 3, and 6. We started numbering from this end. If we started numbering from the other end, the total number would be considerably bigger, which is why we don't. Now, a structural isomer has the same molecular formula as another compound, but a different structure. This thing, if we had 2,3,6 trimethyl-octane, well, actually, we don't need to learn the names for more than 10 yet. So let's do 3-methyl-octane instead. 3-methyl-octane is a structural isomer of nonane. Just plain nonane. 9 carbons in a chain and full of hydrogens. Now you might be thinking, hey, how is this going to count as just sticking on there? Well, you can think of it this way. Originally, if we started with just octane, there was a hydrogen here. And then we replaced the hydrogen with a methyl group. A methyl group is not like methane. Methane is just CH4. A methyl group is 1 carbon and as many hydrogens as can fit, which means 3. So if we replace 1 hydrogen with 1 carbon and 3 hydrogens, then, well, we've added 1 carbon and 2 hydrogens. So if we extend the main chain, what do we actually add? Well, okay, there was CH3 here, but now it's CH2, and there's a CH3 at the end. Which means that that's just CH2. There's a few ways to represent molecules. For example, you can use a ball and stick model. And this is proline. Proline is one of the amino acids. In fact, it is considered a very odd amino acid because, well, most other amino acids have the substituent group, the R group, of an amino acid just sticking out from the central carbon and being just over here doing something on its own. Proline is the only one that bends back like this. It is known to disrupt certain structures in, well, proteins. It is used to break up alpha helices, in fact, and beta sheets too, but that's not the point. Now here we have a space-filling model. This is octane. This is also called N-octane. Why? Because when people were initially classifying organic compounds, they thought like, hey, if we want to have butane, we can have, well, okay, if we want to have pentane, we can have this, or we can have it like this. So they were like, oh, this should be just N-pentane, and this can be isopentane. And if you had butane, if you have a butyl group, like say you have a really long compound, and you had a butyl group sticking out somewhere. So 1, 2, 3, 4. That's N-butyl. And then there is isobutyl. So iso. And then there is sec-butyl. Iso moves this over so that it's 1, 2, 3. And then sec-butyl is down here. And then we have tert-butyl. So tertiary. That would mean just like that. All right, we can also draw structural formulas instead of using these models, as we have done here. This is one form of structural formula. It is preferably not the form you start with. Why? Because at the beginning, your teachers want you to make sure that you actually know that this stands for CH3, CH2, CH3, instead of just thinking, oh, 3 carbons together. If you're just starting out, it's fairly easy to end up miscounting the hydrogens, and that makes for some really irritating and generally dumb mistakes. Alright, so sometimes write condensed formulas. There are several forms, such as just not writing these lines in the middle, and just writing this all in one long splurge. And if you write this all in one long splurge, you would still have to write the substituent groups with a line coming down or going up, as the case may be. And the substituent groups can be laid out to go parallel to the main chain, or it can just stick out and then you keep on writing. This depends on teacher preference and, of course, on regional conventions. Now, alkanes have many structural isomers for a given formula, once you get past just having a few carbons. For example, think about propane. How can you isomerize propane? Well, I mean, clearly, if it's butane, you have one isomer, as is here after we added this part. Now, if we add this methyl group, we have to remove a hydrogen here, because we don't want to end up bonding this carbon to, well, 5 different things. That would be bad. Now, butane obviously has this one isomer. What about propane? If it's just 3, well, there's no way to isomerize. You can't cycle it. You can't make it cyclic either, because that would result in losing 2 hydrogens. It would not be an isomer. What about ethane, i.e. just 2? Well, of course, that doesn't work either. Methane, just 1. Of course, there's no isomers for just 1 carbon. So it's only butane and on up, in terms of carbon number, that you start getting isomers. But the number of isomers piles up extremely quickly. Now, on the subject of naming alkanes, well, I mean, because people wanted to study these and classify these, of course they had to come up with names for them. So, when we name alkanes, of course we need to start with the chain length. Why is this seemingly obvious? Well, if we classify this as an ethyl 1, 2, 3, 4, 5, 6, 7, 8 ethyl octane, that's, well, I mean, you could call it that, but properly this should be called a methyl nonane. Technically, this is a 3-methyl nonane. Now, the longest chain takes priority. So in this case, it's this one. But if you draw the diagram such that this chain is longer, then it will be the other chain. The longest chain is not necessarily the one that seems to stretch horizontally across the center of the page, or center of the problem frame. Be careful. Now, we have 1 carbon as the longest chain, as in just CH4. That is methane. And the substituent would be methyl. For 2, you have ethane. And then ethyl. For 3, propane and propyl. Now you've probably heard of isopropyl alcohol, but wait a second. There is no isopropyl unless you are talking about a substituent. So, Why is it called isopropyl alcohol? Well, let's see. If we have one propanol, the alcohol group is OH. So propyl and then OH. What about 2-propanol? 2-propanol would have the OH or propane 2O, depending on preferred convention. These are all accepted. You would have this. So, this is called isopropyl alcohol. Now, methyl alcohol, also known as wood alcohol, is capable of causing blindness in humans because the body metabolizes it into formaldehyde. Formaldehyde is not healthy. Now, ethane, well, the alcohol counterpart would be ethyl alcohol. And do you know why we use isopropyl alcohol for rubbing alcohol instead of ethyl alcohol? It's because ethanol is the alcohol that people drink. And they want to prevent people from taking alcohol and getting drunk on it. Rubbing alcohol, isopropyl alcohol, is not safe to drink. Now, I do note that you can sterilize a wound, or at least clean it, using, say, vodka can have up to about 50%-ish, unless it's been distilled further, alcohol content, which is, of course, quite useful at killing bacteria in a wound. Now, propane, we do note, though, that the absorption of alcohol, ethyl alcohol, through an injury, it tends to be greater than for isopropyl alcohol. And as a result, the patient may seem a little bit off, so to speak, if enough alcohol managed to make its way into the injury. Especially because, very importantly, unlike the digestive system, alcohol that makes its way through an injury does not pass through the liver first before reaching, say, the brain or the heart. The liver actually manages to filter out most of the alcohol that you drink on the first go, from the intestines to the liver, the hepatic portal vein it is called. Now, next we have, well, we talked a little bit about butane up there, or butyl groups at least, so and I will omit the details here in favor of pent, and you can guess what goes here, right? And this is also pentyl. After that, well, okay, we know pentagons and then hexagons. So, hexane. Hexane is actually considered the standard form for gasoline, even though gasoline is rated in octanes. Well, it's usually considered the standard form. Regional conventions may vary. So, well, we have hexyl. So hex is the 6. And then we have hept. Why it's not septane, I'm not sure, but the convention is heptane, or hepto. And then for octagons, we know that they're octagons, therefore it is octane. So here, octyl. And then Or if it's an alcohol, octol, because OL is the ending for alcohols. Of course, then you would probably need to write 1 octal or 2 octal and so on. So, 9, nonane, nonil. And 10, we know that a decade is 10 years, so decane. Now there are 2 readings for deco. You can read it deco or deco.